Welcome to this tutorial, which is an introduction to SimNIBS. It's given by my colleagues Uda Pointy and Guillaume Sadonino and myself. My name is Axel Thielcher. The introduction comes in 3 parts. I'll cover the first part, where I'll introduce the basic workflow, how to generate an electric field simulation using SimNIBS. I'll demonstrate that actually using our graphical user interface. And while the simulations are then running, the calculations are running, I'll use the time to introduce a little bit of terminology in order to make it a little bit easier to understand what the different output names actually mean when looking and finally at the results. After that, my colleague Uda Pointy will take over. He will talk about how to model heads, head anatomy based on MR images and what you should care about when doing that. And after that, Guillaume Sadonino will talk about how to systematically optimize electric fields induced by brain stimulation. This would be a general workflow. Usually we start with images of the subject, like here shown, a T1 weighted image and a T2 weighted image. The T2 weighted is optional, but we recommend to use it to have robust segmentation results, particularly of the skull region. And we use those to segment the images and then to measure to have such a head model here. This is now an anatomical head model where it's indicated that here we would have skins, muscle compartments, we would have skull, here CSF, gray matter, white matter. And this is not fully sufficient. We still need to do a few more things. First of all, we have to convert this anatomical model into a physical model by saying assigning conductivities, basically saying, okay, when you're here, then the head has a certain conductivity. When you're here, it has another conductivity. This would be, for example, a scalp. This would have a conductivity of around 0.4 Siemens per meter. The blue one would be skull. That would be a very low conductivity here of 0.01, as you see. And the red ones, for example, would be the compartments with the best conductivity here in the head, which would correspond to CSF. And the gray and white matter of the brain are somewhere in between. Once you have done that, it's still not you're still not fully ready to start a simulation. You obviously also have to tell where the TMS call is on the head, or alternatively, when you do an electric field simulation of electric simulation, then you have to assign, basically, you have to set where the electrodes are on the head. And you also have to assign the currents flowing into those electrodes and flowing out again. Or for the TMS coil, how strong the current flow through the copper windings of the coil are. Here for the electrodes, they also consist of conductive materials, which are also modeled here and attached to the head. This is done for each simulation newly. So this step, which is the most time-intensive step to create this head meshes, you only have to do once, and this adding of electrodes is only done when it's needed. Basically after you have set the simulation up in the graphical user interface. Then you're ready to run the simulation. We use the method called finite element method for the solving the fields. There are other alternatives out, like the binary element method, in order to get to the result, which is shown here for one example. This would be now your output, which you most likely interested in, the electric field here on the brain surface. Actually, the calculation results represent the field in the complete head here. Usually we restrict the visualization only to the part which you're interested in, which is in the brain. But you can also explore the other parts if you have certain interest in that. This is another view of the pipeline. Again, we would start with the images of the subjects, which we then would run through the head modeling procedures. And again, Uda will talk about that more later on, to then set up the simulations in the graphical user interface. That's something I'll focus on here. And then also I'll focus on how to then look at the results of the simulations, which then run automatically using a viewer called Gmesh or also FreeView. If you want, you can also have information from diffusion tensor imaging, which can be helpful to inform you about the conductivity of the white matter compartment. Because white matter is very structured, has very structured fiber bundles. It's thought that the conductivity is also anisotropic, and it's thought that diffusion tensor imaging actually can be used to inform you about the conductivity anisotropy inside white matter. So when you have a diffusion tensor image of the brain, you can use it to estimate the conductivity anisotropy and use that to assign that to the FEM calculations. This is again an optional step. When you don't have your own T1 or T2 weighted images, then we also provide a few example head models so that you can get started easily. So let's start with setting up a simulation. For that, I pause here the presentation. And we go to the graphical user interface. First thing is to select our head mesh. With our example data set, we provide 3 different head meshes. One is a simple sphere, one is the MNI head, and one is the so-called ERNIE data set, which I'll work now in the following. Each of these data sets then contain an M2M folder, which contain the actual detailed information of the heads. So ERNIE has this M2M folder, so select this one and wait a little bit until the data is loaded. So now we are ready to set up the simulations. What you see here is the scalp of ERNIE. You can also look at the brain. And it's relatively easy to set up simulation now. Let's start with a TDCS simulation. Just clicking this button brings up this list of positions, currently empty. So let's add an electrode and assign it a position. Let's say we want to stimulate our C1. So we could just now set C1, position of it. When we're not fully happy with the orientation of the electrode, we can change that later on. Let's first assign a shape. Now we have a 7 by 5 centimeter electrode. We can preview its shape. As you see, there's a certain distance here to the scalp. This is because it's just a preview. It's not the real electrode model, which is then added to this head mesh once you start the simulations. This preview is just to help you getting an impression on how the electrode looks like, how large it is, on its orientation. So here it's now orientated like that. You might want to orientate it a little bit more to follow or be aligned with the direction of the central sulcus. And that you could, for example, do by changing its position simply by double-clicking. So double-clicking here, double-clicking here. And now we have changed that. Yeah. Let's also define a return electrode, maybe here above AF4. So let's add another electrode. Let's try whether AF4 is good. Otherwise, we'll update it later on. You can actually use the same shape. Yeah, the shape looks fine. Maybe the direction not so nice. So let's update that one. Can preview. Yeah, better. Maybe one more time. Okay, that looks fine. Now we are more or less ready. Obviously, we still have to assign the currents which flow into the electrodes. Let's use here 1 milliampere and -1 milliampere for the return electrode. And then we're done with the TDCS simulation. Let's also set up our TMS simulation, where the first thing is to define a call which you want to use. Let's use this MaxStim call here, for example. It's a pretty standard double coil. And again, we have to define positions. For example, we could say, well, let's use C1, as it seems to be roughly above the hand knob, and this is not fully satisfactory for us. We can also improve it a little bit by again defining an individual position, maybe directly above the hand knob here for TMS. So that looks quite nice now. Now we're ready. You might see this skin distance. So what it means is that we don't assume that the TMS call is directly here on the skin, but that the TMS call has a little bit of distance, namely 4 millimeters to the skin. The reason why we do is that we try to take into account that people obviously also have hair, or there might be some cap which they wear during stimulation, for example, to attach the DRF of the neural navigation system. But feel free to alter that when you have more detailed information or when you think it's not appropriate. Just report it in your simulation results. Then we also have to define the strength of the current in the TMS coil, or more detailed, the rate of change of the current in the TMS coil. And for TMS simulators from MacVenture, it's actually relatively straightforward. You just look at the panel. The panel states you directly this value, and you can just copy it over. For other stimulators like MaxStim, it's a little bit more involved. There, the stimulation intensity is defined in % of the maximal stimulator output, and then you have to convert that value to the DIDT value with a little equation. If you're only interested in the shape of the field and you don't care about its absolute intensity, then you can just leave it here at its standard value. Otherwise, when you want to really have individual electric field strength estimates, then you have to enter the proper value here as well. But that is all we have to define there. So now we define bond coil orientation. We could have several of those, which would then just have result in 2 or 3 or 4, depending on how many we defined, simulation results, which you can then look at or analyze separately from each other. So now we are ready to run, and the results will be then placed in this output directory. In case this would already exist, the graphical user interface would complain because you don't want you to unintentionally mix up simulation results from different runs. Then you would have to give a new name. Last thing before I start is that I want to highlight a little bit the simulation options which we have. As standard, we simulate the electric field. That's why these 2 things here are tipped. We can also instead simulate the current density, or both. They are more or less telling you the same story, because they are the current density and the electric field are related to each other by the conductivity. So once you know the current density and the conductivity, you can calculate the electric field, or vice versa. There are a few options to tick here. Instead of just looking at the results here on this head mesh directly, you can also look at it on its individual cortical surface. I'll explain a few things about that later on. Or you can take it further to group spaces, like the average space, which is average cortical surface of many subjects, basically, so that you can do group averages of fields on these surfaces there, for example. If you prefer to work further with the fields in nifty volumes, you can also do that. This would be just as individual output, or you can also transform it to MNI space. and do your analysis there. I'll now tick here all three so that we can then look at the output results, which are stored in different subfolders of this folder here, and explore them a little bit later on. And with that, I'm ready to start this simulation. And here we go. And I'll use that time to go back to the presentation to explain a little bit about the terminology. When looking at the results of electric field simulations, then it's useful to realize that electric fields are vectors, so they have both strength, which is here indicated as the length of this vector, and the direction. And then the question is what the interesting parts are to report. First, a little bit about how we name them in SimNIBS. So the electric field strength is mathematically also termed as the norm of the vector. That's why we call the electric field strength, which is just length here, the norm E or E norm in some of the results also. And as alternative, you might be also interested in looking at the direction. And one useful direction is actually looking into the amount of the current, so that would be the electric field, the total electric field, the amount of this electric field which either flows into the cortex or out of it. So this would be the local orientation here of this part of the parameter. And we want to look into the, or we are interested now here in the part which is either flowing perpendicular or also normally into the parameter or out of it. That's called E normal. The same naming convention is also followed for J, where the length of the J vectors, so the strength of the current density, is again called norm J, versus the part of the current density which either flows into the cortex or out of the cortex is called J normal again. In electric stimulation, this is also called an anodal stimulation here in red, or that would be correspond to the cathodal stimulation of this cortical sheet here. So what to report then? For TMS, well, first of all, we think that in TMS, we mostly stimulate the cortical sheet. This is here one representation of a cut through here through the hand knob area of the subject, nicely visualized with the different types of neurons here, taken from the publication from Abera, from the Petershev group here. And what we think happens in TMS, at least according to this model, this very detailed model, and also matching basically experiments which systematically compared electric fields with MEP changes above the motor cortex. What we think here is that the neurons are actually stimulated at the ends of the axonal collaterals, and because the axonal collaterals have many different orientations, it's actually not so important how the field is directed. So to a first rough approximation, we think that the electric field strength is the dominant factor which determines whether neural excitation occurs or not. This is also again visualized here. This would be the representing the neural excitation strength here for these neurons, for the pyramidal cells here, which just by visual comparison corresponds nicely with the electric field strength at these positions. So to a first approximation, we think that we can report electric field strength distribution to get a rough idea on where we stimulate in the cortex. I'd like to highlight here that also there are other hypotheses. Some think that the normal component, so basically the part of the field which flows into the cortex locally or outside the cortex, is the important part. For electric stimulation, we have the concept that we have a cathodal or anodal stimulation. This stems already from these very early experiments from Bindman, where we lead currents normally through the gray matter sheet, and by that either increase or decrease baseline firing rate. For cathodal stimulation, we decrease it. For nodal stimulation, we increase it by this currents. What we think happens there is that by this current flow, either inside the cortex or out of the cortex, we polarize the pyramidal cells so that their soma is either a little bit depolarized, which would then enhance baseline firing. At the same time, that dendritic tree would be hyperpolarized a little bit, or vice versa. When we shift the currents around or the electric field around, then the opposite would happen. Then the soma would be slightly hyperpolarized, while the dendritic trees would be slightly depolarized. So there we expect to have a certain directional effect depending on the normal component of the electric field, and that's why it can be useful to also look at the normal components instead of only the electric field strength. Again, physiology is quite complex, so this view is simplified. We know that also electric fields perpendicular to the neurons here can affect neural activity, likely by polarizing the axon terminals. So again, it might be interesting to not only explore this component, the normal component, but also other components of the electric field. How does it then look like? As to give some example here. So when we look at the electric field strength, here for a bipolar F3-F4 montage, as for example tested for depression treatment with TTCS, then we see that, well, we have electrodes here, and even though we try to focus stimulation here on this part and also on the contralateral side, we see that we actually have very strong currents here also in other or electric fields here at other parts here of the brain. When we look at the normal component, we see a quite interesting pattern because we have a current in the systematic outflow, inflow, outflow. So we would have a cathodal stimulation mostly here under this electrode. Then, because the currents have to basically flow here in this direction from here to here, we then have an inflow of the currents here in the hemisphere cleft, as seen here on the right hemisphere. Well, when they flow into the right hemisphere, then they have to flow out of the left hemisphere here on that side. So here we would have again a cathodal stimulation, and on the other side we would have again a nodal stimulation. So we have like a plus minus pattern here, which makes the interpretation of this whole montage relatively complicated because it's, for example, thought that also areas here in this region are really important for important regions for which are affected when people suffering from depression. So even though this montage was initially designed to stimulate DLPFC, it does much more complex things most likely. Again, this is just a hypothesis now derived from this electric field pattern, but at least this can highlight us to the fact that it can be very useful to explore those field simulations to come up with possible hypotheses on how certain montages might result in specific physiological and behavioral effects. With that, I'd like to end this slide presentation and go back to the simulation results. So the simulations have finished as shown here, and this then now resulted in a lot of, or a few fields here visualized in the viewer. I'll go through them in a minute now in more detail, so I just close them for now. This is just a convenience function that you can have them immediately available, but I think it's more useful when we now look into the simulation output folder and take it step by step. As you see, it contains 4 subdirectories, which I'll explore later on. And then it contains result files for 2 simulations, 1 and 2. The first one was a TTCS simulation, And the second one was a TMS simulation where you also find the name of the coil. The output is always stored in the results file with the .mesh endings. Let's look at that. This takes a little bit of time to load. In the meantime, I actually like to highlight a few more output files. First of all, you have here a simple text file which gives a very rough summary of the results. Again, for the two simulations here, 1 and 2. So you get some peak field values here, and you get also some focality values as a result here. And as you see, for example, the TDCS focality is far worse than the TMS focality, which is expected for an unfocal montage, just a demonstration on how to read these values. And the TDCS fields are also weaker than the electric fields of TMS, even though this is not too meaningful here because I didn't scale here the stimulation intensity to the output of the stimulator. I just used the standard values. Usually these values would be still much higher when you scale them properly to the individual stimulation intensity which you need for a specific subject. You also have a log file in case something went wrong. We might ask you to send this. And this is a settings file which you can again actually load into the graphical user interface and then go on modify it there. Or alternatively, you can also actually load that into SimNIBS, into MATLAB or Python and edit it there to adapt the simulation and run it again. But now the results have been loaded. For the TDCS montage, as you see, as expected, you have one electrode here, one electrode here. You have a strong current flow in between, which means that you have also strong fields here, especially at some of the gyro grounds here. Now what we see here is a visualization as a standard here on the pile surface, so the outer surface of gray matter. And you could argue that this might be not too informative because here actually there are no neural cell bodies. Instead of looking at the outer surface, we might rather want to look into the gray matter and maybe something like the central layer or the middle layer of the gray matter surface to have a better impression on the electric field distribution at a position in gray matter where also neural excitation is likely occurring. I'll show you how to do that in a minute. First, I want to go on to actually the TMS montage, also quickly look at the results. So, as expected, the TMS montage is resulting in a more focal field, which is focused here on the hand knob. That's where we centered our curl. You can confirm that by looking at this small visualization of the coil central axis and its main orientation. So that would be a typical field for a double coil. Let's close this again and look a little bit more into detail into this subfolders. Let's start with the subject overlays. What you find again there is you again find two mesh files, one for the first, the simulation result, which was a TDCS field, and the second one for the TMS field. So let's double click this one. Looking more or less like the same because it's the same simulation, but now the electric fields are actually read out here in the central or the middle of the cortical layer, which is more useful likely, also because by that we can actually nicely see into the sulky, which is a nice side effect of that. So this is not an atrophic brain, it just means that instead of looking at it at the pile surface, the outer surface of the gray matter, we have interpolated the field at the central layer. Here, because now we have a surface available, which gives us a clear orientation, we can also look at the normal component of the field relative to the surface. So let's look at that. And then it looks a little bit differently. So here now suddenly things become red and blue for in and outflow. We see that most currents are flowing consistently in one direction here. So they flow to the return electrode. So most of the areas close to that are blue. And here it's getting more red, meaning that they again consistently flow from one side to the other. But you also see that here in the hand knob area, it's actually quite consistent red, not fully here, it's a little bit of blue, but here this part is consistently red. And this might also explain why these montages achieve their physiological effects, because in your target area, in your area of interest, you have a little bit of a consistent stimulation with one polarity, which then hopefully creates some kind of specific physiological effects. You also see that because you have this current flow from here to here, you have a clear-cut red, blue, red, blue, red, blue pattern. Let's look at the same result for TMS simulation. Again, here you see a little bit better into the sulky. Or you could also look into the normal component, which, as said, is probably not as predictive of neural excitation as the strength is. So here it might be more useful to look mostly at the strength of the electric fields. Now here are all kinds of other files, but they actually contain exactly the same information, just stored in another format. Here we would have, for the left hemisphere, the results for the TTCS simulation, so simulation 1. Here we would have the electric field norm, so that would be the electric field strength. Here it would be the electric field normal component, meaning the part of the electric field which flows into the cortex or out of it. And further down, we would have the same for the right hemisphere. The reason it is stored in this format as well is it's actually the same format which is used by FreeSurfer to store curvature data. So in case you prefer to, for example, use FreeView to visualize the results, you can use those, or in case you prefer to use those results for further post-analysis, post-processing, then you can use those. But actually, the data in those files is exactly the same as already stored in those two .mesh files, just your own preference, what you actually prefer. Let's look also a little bit further. There's again an overlays, which means that subfolder, which means that it's visualization on some surfaces. Again, more or less the same name. We have Ernie, which was the subject ID. We have a TTCS simulation, and it was the first simulation. So let's again look at it to see what's different. Well, as you see, the brain now looks massively different, and this is because it's not the individual cortex of the subject, but it's the average template where the results were mapped onto after they have been calculated for the individual anatomy. And this can be quite useful when you want to do group analysis. Here you can, for example, make a group average electric field quite easily by transforming them onto this FS average template and then doing an average. Again, you can also look at the electric field normal component. And you see this red-blue pattern, which now doesn't follow the gyrification anymore closely. This is simply because this is an average brain here, where much of the detailed anatomy is actually lost. But what you see still is that here in the hand knob region, you have this red region, and on the other side, the blue region. So the big landmarks are still maintained. You also still see that when you are here closer to the return electrode, you actually have more blue. And here you do have more red. So this is, again, just another way of visualizing the results here on this average anatomy in case you want to go further and, for example, do averages of the fields of several subjects. The same again for the TMS. Centered here on the hand knob. And similar to the output folder before, we have all these sub results, which are again in free surfer format in case you prefer this format for analysis of the results. Otherwise, you can just stick to the .mesh results. The last thing is that often nifty volumes, so voxel space is preferred. We also support that. We can look either into the individual space of the subject given by the individual T1. Again, here the two different simulations, the TTCS simulation and the TMS simulation, either the electric field as vector, so this is a 4D file with X, Y, Z components of the electric field, or here the norm of the field, so the strength of the field. Normal components, so the part which flows into the cortex or out of the cortex, is missing here because here in a voxel format we don't have a surface orientation, so we can calculate that. These results we can also take further to MNI template, for example, to doing two kind of groups analysis. So again, the same nomenclature. So with TTCS and TMS for the 1 and 2 simulations, now with the addings of MNI, that is clear that's in an MNI space. And the last few minutes I want to use to look a little bit into those results using Freeview here. So first let's look into this T1 of the subject. This is the individual T1 of Ernie, but morphed nonlinearly onto the MNI template. This would be the MNI template. This would be the T1 of the subject. When you have such a simulation folder, here the M2M folder, then you have a 2MNI folder. And inside you have then this file, which I already have opened, which is then the T1 again, but now in MNI space. There are also a few more files. One is the gray matter MNI file, which is also created as a standard thing. And I load that now because I want to highlight its use later on then a bit. So now let's also actually just go to the simulation results, which are stored here. Let's go to the MNI volumes and, for example, load the TTCS electric field strength and also the TMS electric field strength into Freeview. So what you see here as a first thing is that, well, maybe the first thing is to change a little bit the color map here. And let's start with the TMS simulation. You see in general that the fields are somehow focused here. This is basically where the coil was positioned, but the fields are calculated in the complete volumes, and they're also stored in the complete volume so that you can see the fields actually in skin, in the skull, and then also in the brain. Yeah, usually you're only interested in the brain, so you might then want to actually adjust the intensity scale to highlight more the parts of the field which are in the brain. And then it gets, so here you start seeing now, this would be now our proper scaling. And then you see that obviously the fields here are really stronger. So it might be nice to be able to mask the fields a little bit. And that's why we have included the gray matter mask here in the MNI space. This is not automatic, but what you can do now is you can basically load mask and this result in Python or MATLAB and just apply this mask to the fields to only have the field in gray matter. And why this is particularly useful is that we have here individual anatomies in MNI space, and they obviously are co-registered also the MNI template, but they're never perfect, as you see here. So this is the individual gray matter space, and in the background we have the MNI template. In some positions it fits better, but actually here it would be more in the CSF of the template, but here it's clearly the hand knob of the subject. So and when you have several of these subjects, then the gray matter will be a little bit different. And because the field distribution depends on the distribution of tissues and scales directly with that. For example, we see here that the fields here for team S are generally stronger in white matter, or maybe go here, than they are in gray matter. It's actually good to have subject-specific masks in MNI, which we can easily apply to the simulation results, to then only look at the specific field of the subject in MNI space, which is also really corresponding to gray matter, namely the tissue where we know that we stimulate. So let's do the same with TTCS. Here, it's quite astonishing to see that the strongest fields are actually not in the brain, but in the skull. And this is simply because we have a strong current, or the currents have to go from the skin through the skull into the brain. And because skull is very low conductive, this causes this quite strong fields inside the skull. But when we change the scale slightly, then we see that we now have the fields in the cortex, again back. Again, we're not really interested in those. So instead of reporting or looking at the fields here in the skull region, we might rather apply this individual gray matter mask in MNI space to those field results, and then specifically only look at the resulting field, which then would correspond to the field in gray matter, and also not in white matter, because we're relatively sure that we don't stimulate in white matter when we talk about TTCS. So these are not the most pretty visualizations now. The main part here, which I wanted to highlight, is that when you transfer results to MNI space, then they obviously don't fit perfectly. The field simulation results don't fit perfectly to the MNI template, simply because the registration will never be perfect. The individual anatomy just contains more details than the template. In order to account for that and not mix the fields from different tissues like gray matter, white matter, or CSF, we supply, or we suggest that you also use this gray matter mask, the subject-specific gray matter mask, to only read out the electric fields inside this gray matter mask, and then go on with the analysis from there. For example, could intersect this gray matter mask and further with a region of interest in MNI space, so that you have an average field in this region of interest for this specific subject, which only corresponds to the field which is then in gray matter. And with that, I'd like to stop this part, or end this part of the introduction, and hand further on to Ula for the next part.